Where we left off in the last video, we were starting the proof of this theorem that allows us to integrate characteristic functions with respect to product measures. Before we continue, let me remind you that you can support the channel in a few different ways. All the links to the different ways of supporting us are in the description of the video, but I would especially recommend that you become a member of our YouTube channel. Just by paying £1 per month, you can become a member and get access to exclusive content for members only. So again, links for that in the description of the video. And now let's continue with the proof. What we did was we defined this set M as a very big set of all the sets in the sigma algebra that satisfy what we want for the theorem. What we wanted to show was that every element in the sigma algebra was an element of the set, because we want to prove the theorem for all the elements in the sigma algebra. Now we found a problem. That problem was that if I try to prove this using the knowledge we had from sigma algebras, the statement that M is a sigma algebra may not hold. And so we have to change our tactic by going to monotone classes. So now our proof will change, and what we're going to do is we will prove that the product algebra is a subset of M, and that if M is a monotone class, that is, it satisfies these two properties, then we're going to have for free, just by the monotone class lemma, the result, the inclusion that we want. So now let's start by proving these two things, A and B. Remember that our algebra is formed by rectangles. So we want to take an arbitrary rectangle and show that it's in our monotone class. Showing that something is in a monotone class means showing that it actually satisfies the properties of the theorem, that these two functions are measurable in their respective spaces, and that integrating these functions will give us the measure of the entire rectangle. So let's take a rectangle. Let's call it E. E is a rectangle in our product algebra, so it's just going to be the product of two sets. Let's call them X and Y, where X is in the sigma algebra of X and Y in the sigma algebra of the space Y. Take a generic rectangle. So this is just an element in the product algebra, and we want to show that E is in M. So for that, let's start by defining this function f of x. F of x was the measure nu of the x section of E. So this is the measure nu of, and let's remember what it meant, Ex. Ex was the set of all the points y in our space Y, such that xy is in our set E. But remember, we just said E is x times y. So we need this to be true. We're measuring the size of this. But now this is, of course, the same as measuring the size of all the y in y, such that, well, we need x to be in x, and we need y to be in y. And because this is only measuring the points in y, this condition will come out of the measure as a characteristic function, because we need this to be true. So we still need the condition x in x. So this is going to give us the characteristic in x of the point x times the measure nu of the set y. And now, by a very similar argument, g of y, remember this was the measure mu of now the y section of E, and this will be, by again the same things, just gonna be now the characteristic on y times the measure mu of x. So it's very simple to see already that these functions are measurable, because x and y are measurable, so these two characteristic functions are measurable, and then these two other things are just constants. So we already have this first property that we need for the rectangle E to be in M. This first property is already true, but now we need to check if it also satisfies this condition. So for that, let's try calculating each of these integrals, and let's see if that happens to give us the measure of E. So we're going to start with the integral of f with respect to mu, because f is a function of x and mu is the measure in the space x. What is this? Well, we just said that this function f is the characteristic on x times nu of y. So we are integrating the characteristic on x times nu of y. And all this with respect to mu of x. Now, nu of y is just a constant, so we can take it outside of the integral, and then we're integrating the characteristic of x with respect to mu. So that is the measure mu of the set x times the measure nu of the set y. So now we have a product of these two things, just by definition of product measure. Because E is a rectangle, we have that this is directly the product measure of the set E of the whole rectangle. Okay, but now doing the same for G, if we integrate G with respect to nu, well, we use this same property and the same argument will give us exactly the same. Mu times nu of the set E. So this is great because this is exactly the second condition that we needed for E to be an element in M. So E, therefore, is in M. And this implies, because E was an arbitrary rectangle, that the product algebra is a subset of M. And this is A. This is what we wanted to prove for A. Now we need to prove that M is a monotone class. So we need to prove that this set that we just defined satisfies these two properties. When we take an increasing sequence of elements in M, the union is in M. And when we take a decreasing sequence, then the intersection is in M. Let's start with P and property 1. So we're going to take M1, M2, and so on, all elements in the set M, such that M1 is the smallest, so it's contained in M2 and so on. And what we want to show is that the union of all these elements is also in M. Now, these elements M1, M2 are all in M. That means all of these sets satisfy these two properties of the theorem. So I will have one of these functions for each Mn, and then we will have this property also for each Mn. And we need to show that it holds for the union. So let's start by giving all these functions that we know exist and satisfy these properties some names. So let's define Fn of x will be the measure nu of, well, for the set Mn has to be the x section. The same for G. Gn of y is going to be the measure mu of, and now for each of these sets, the y section. So we already know everything about these sets because these are all elements in M. And we want to say something about the union. So why don't we define f of x to be the measure of the section of the union. So I will take the union and I will take the x section, of that, and then I take the measure nu. And the same for g. G of y is going to be the measure mu of, I will take all the union, and then to all this union I take the y section. So I know everything about these functions fn and gn, all the properties they satisfy because they are already elements in M, and I want to prove that the same holds for f and g. Now, a key thing over here is that this sequence is increasing. So because this sequence is increasing, then fn is an increasing sequence of functions to f, and gn are also increasing towards g. So this is already giving us a huge hint of what to do. Well, what is my objective? Well, I want to see what happens when I integrate the function f, so the function of the union, with respect to mu. Well, but I know that I have this sequence that is increasing to f, so I can use the monotone convergence theorem and say that this will be the limit when n goes to infinity of the integrals of each of the f sub n's. But now each of these integrals, because the sets mn are all of them in our big set M, then we know that each of these is the measure of the whole set. So I will have the limit when m tends to infinity of the product measure of the set Mn. Again, this is because these sets are all in the big set M, and I define these functions in the same way that the functions we knew we had in the theorem. So now we have this limit of the measure of some sets, and these sets, because of how we define them, are increasing. So this, just by properties of measures, will be equal to the measure of the union. And this is exactly what we wanted to show. Well, in the same way, now for g, we can integrate g with respect to nu. And again, using the monotone convergence theorem, we can say that this will be equal to the measure of the union, which is exactly what we wanted because this shows us that this set satisfies this property here. Now E is the union of all these mn's, so this union is an element in M. So that shows that when I took a sequence of elements in M that was increasing, then the union is in M. Now we would need to show that when we take another sequence now decreasing, then the intersection is in M. But the proof for that will follow very similarly. Again, we're going to use the monotone convergence theorem, but we will need one extra fact. To prove 2, it will follow similarly by monotone convergence theorem, and now it will be essential that we use that the measure of x and the measure of y is finite because we have an intersection. Because now these two measures being finite implies that the measure of the product is also finite. So I will leave this proof to you. It should follow very similarly to what we did for the union, but at some point here in the end, when we take this limit to be an intersection, we are going to need the finiteness of the measure. So now that we have 1 and 2, this proves that M is a monotone class. We showed that the product algebra was in M, and that M is a monotone class. So now, again, just very simply by the monotone class lemma, which I am not going to prove, we have immediately that the product sigma algebra is a subset of the set M, which is exactly what we wanted to show for the theorem. Now all of this works when mu and nu are finite measures. If we go to our theorem, the theorem says that this holds in more generality. It holds for sigma-finite measures. So now let's do the second case, which will finish our proof. So if these measures are sigma-finite, then what this means is that we can write our product space, so the product measure will be sigma-finite, and the product space can be written as an infinite union of sets x n times yn, where each of these xn is in the sigma algebra of x, each of the yn is in the sigma algebra of y, and they satisfy that the measure of each of them is finite. So what we can do is we can apply everything that we did for these sets xn and yn, and then just use the monotone conversions theorem. Now once we do this, we finish the proof of the theorem. I will leave this part to you because it shouldn't be too difficult, but all the hard work was in proving all these things, and especially in realizing that by having these two properties for this set M that we constructed, it immediately gives us the result that we want by the monotone class lemma.